Hello and welcome back to IET 301 Engineering Project Cost Analysis. In this lesson we're going to quickly go through Chapter 2, provide you an introduction of profit, loss, and revenue, as well as the different types of costs that you'll encounter in this course, and provide a few introduction to estimating techniques. For those of you that have already started on the course, you know, or will have recognized that the homework assignment for Chapter 2, that is homework number 1, tends to jump ahead a little bit, and we'll talk about that near the end of this lesson as well, just to give you an idea of what to expect on that assignment. So, Chapter 2 is labeled Engineering, Estimating the Engineering Costs and Benefits. What you need to realize is that engineering economics is all about estimating future benefits of a decision. Therefore, everything that we do in engineering economics is an estimate. So as we go through this class, we should go through and say, okay, well, because this is an estimate, it's just a predictor of what is going to happen if we make this decision. It's not set in stone, and that's incredibly important to recognize. So as we go through, what we need to do is define a few fundamental terms. In fact, a lot of the stuff that we do in this chapter is based around defining these terms. So the first thing we're going to define is revenue. Revenue can be defined as the total income received from a particular source. So the total income received from a particular source. Geez. I suppose while I'm doing it, I'll fix that one too. So C, I'm not sure if that's any better. No, it's E before I. EI from a particular. Okay, the cost then represent the money needed to produce a product or offer a service. So it's the money needed to produce a product or offer a service. And then finally, the profit can be defined as the excess in returns versus expenditures. If we consider the revenue, the returns, and the expenses, the cost, then we can simply say that the profit of any activity is nothing more than the revenue minus the costs associated with it. We'll see here in a few minutes that, in fact, we can use this basic idea to go through and look at profit and cost modeling to see when a production cycle is profitable, when it will lose its money, and where that break-even point is in that model. So I'll go ahead and define the break-even point now. Break-even point is the point where the profit is equal to 0 therefore the revenue equals the cost. Okay, so before we get to the modeling of the profit cost diagram, we'll go through and identify some of the different types of costs that we'll run into in this class. The two primary types of costs are the fixed cost and variable costs associated with the production line. So types of costs. Okay, so we have fixed costs. And this is the, oh geez, how did the book define it? The constant or unchanging cost that is not affected by quantity produced. You'll see in the homework that an example of the fixed cost is the rental of a room or a facility. That rental is not affected by the quantity that is serviced by that room or that facility. It is a fixed cost that is unchanging based on the quantity that you run through it. Okay, the variable cost then represent the costs associated to produce each piece of product. If a widget or whatever costs $5 to produce, then we'd say that the variable cost is equal to the $5 per unit times the number of pieces produced. Okay, from this then we can say that the total cost, so I'll say C sub T is equal to the fixed cost, C sub F, plus the variable cost times the quantity produced. You'll notice that the textbook actually uses Q to represent quantity. That's fine, I just like to model stuff on a graph, so I usually represent my independent variable as X and make everything related to X. Now, this is not the only type of cost that we have. We also have marginal costs. Okay, marginal costs represent the cost of producing one more unit. Good example of this is when you consider how many credits you're going to take in the quarter. You know that if you take between 12 and 18 credits, it costs you the same amount. So the marginal cost of taking 15 credits associated with taking 16 credits is actually 0. Therefore, we can say that in that instance, the marginal cost clearly indicates that you're better off taking that one additional credit because it's not going to increase the total cost associated with your tuition. Okay, the average cost then is nothing more than the total cost associated with producing a number of units divided by the number of units produced. Example of this is if we have $800,000 used to produce 10,000 units, we see that each unit costs $80 to produce. Okay, so this gives us a real quick introduction to the types of costs. Now we will talk about a few more types of costs, But before I do so, I want to get to that profit loss diagram that I mentioned a second ago. So a profit loss diagram provides us a graphical representation of a production or other income streams. So I'll say the graphical representation of a profit and loss. Function. What you'll see is that in each case, you will have the horizontal axis representing the number of units produced. We will have the vertical axis representing the money, the cost for revenue generated. So this is defined in dollars. And what we will then have is two functions represented on this graph. We will have one graph that will represent the revenue of the particular activity that we're performing. A second graph that will represent the cost of that activity. And remember, cost is equal to the variable cost plus the variable cost times the number of products produced. So C sub B times X plus the fixed cost. The revenue then is going to equal the per unit revenue. So R sub U times the number of units produced. And what we see then is that in this case we have three primary regions. Okay, we have the region where the cost is greater than the revenue, and this is the region of loss in our activity. Okay, we have the point where the costs equal the revenue, and as I've already defined, this is what's known as the break-even point. That's where our profit is zero and our revenue equals cost. So this is the break-even point. And then we have a region where revenue is greater than cost, and this represents our profit region. And as we all know, that's the region where we want to continually operate in. In this case, I use linear or lines to represent my profit and revenue functions. However, keep in mind that this isn't necessary. You can have parabolic, you can have cubic functions. Any number of different types of functions can result. You can have piecewise functions, which is not uncommon. So in the homework, you'll notice that one of these that you do ends up with a parabolic or a quadratic type of curve. You just have to go through and analyze it the same way. In the region where the cost is greater than the revenues, you are in a loss region. In the areas where your revenue is greater than your cost curve, you're in a profit region. So keep that in mind. Okay, so this should help you out with that profit loss diagram. In addition to this, what you see is that there are several other types of loss associated with or that are introduced in this chapter. We have what are known as sunk costs And these are costs that are expenses that have already occurred. Okay, one of the things that I tend to do on occasion is think back and say, oh, well, if I had not bought this, or if I had bought this when it was cheaper or something like that. When I purchased something in the past, that's a sunk cost. There's nothing I can do about it now. I might be able to try to sell it to recover some of that money, but the fact is it's sunk. In the case of engineering economics, since we're typically trying to analyze the future benefit of some present decision, we hardly ever analyze sunk costs. These are things that are in the past that we cannot change now. Okay, opportunity cost represents the cost of engaging in one activity versus another. Ideally, what we'd want to do is make sure that we're always engaging in the most lucrative activity. However, if we have two activities, we can go through and analyze the opportunity cost of choosing one activity over the other. If we do in fact choose one activity, then we encounter what's known as a foregone opportunity cost, because once we choose one activity over another and engage in that activity, the other opportunity is gone to us. It's no longer available. We've already decided our path. The opportunity cost of that other is no longer available to us. Several other things that we are introduced to in this chapter are recurring costs that periodically occur. Okay, and a good example of this is maintenance. And I better say scheduled maintenance. We should be changing the oil in our equipment periodically. We should be making sure we replace the tires periodically. We could consider registration and licensing of equipment a recurring expense because it occurs once a month or once every 6 months or once a year. Okay. We also need to consider non-recurring. Costs, and this would be an example of a equipment failure, so unplanned maintenance. Along with that unplanned maintenance, of course, we have a productivity cost as well. So anytime we have maintenance that is unplanned, when determining the non-recurring costs, we should also determine how much cost was associated with the lost productivity that was, or of the productivity that was impacted. Okay, we also, the last type of cost that we're introduced to is incremental cost. Incremental cost provides you a way of analyzing two different alternatives. Let's say that alternative A costs $10,000, alternative B costs $12,000. The incremental cost between these two alternatives is $2,000. So what we see is that going from alternative A to alternative B will cost us an additional $2,000 to choose that alternative. Okay, so with this then, we're done taking a look at the costs associated with this chapter. Next, I'll go through real quick and talk about the types of estimating that we'll do. Before I do so, I'll go ahead and toss out there this idea of present value and future value. In our next lesson, chapter 3, we'll go into this extensively. However, for a couple of the homework problems associated with chapter 2, that is on homework number 1, you see that this idea of present value and future value comes in every so often. So just as a quick introduction to this, we can say that the present value, or I'm sorry, I will say that the future value of something is equal to the present value of that thing, or of that monetary instrument, times 1 plus the interest rate raised to the number of periods that it is assessed over. Good example of this is, let's say that we want to determine the future value of $10,000 that is put into an interest bearing account at 1% interest and left in there for 5 years. What we would say then is that we have $10,000 times that should be 0.01. We know that 1% interest is the same as 0.01 as a decimal. So 1.01 raised to the 5th power. When we go through and punch this into our calculator, then we would be finding the future value of that investment in that particular account. So for several of your problems, you'll see that you need to determine the future value given some present value of the particular activity. I believe this is problem number 4. When you first see this, you in fact use it twice on assignment number 1. Keep in mind it's kind of frustrating because the author does pull a little bit of information out of chapter 3 in order to present this first homework assignment. Okay, so now let's briefly provide an overview of several estimating processes. First off, the estimating process is important to us because engineering economics is all about estimating future So it's all about estimating the future worth of a present decision. Okay. So there are 3 types of estimates. There's what's known as a rough estimate. Typically this is used in construction. This estimate has a accuracy somewhere between -30 to 60% over. So it can be downwards of 30% under the actual cost up to 60% over the actual cost. Again, this is used in construction quite extensively, just to give a real quick idea of how much a project will cost. There are what are known as semi-detailed estimates. These estimates are between 15 to 20% accurate, so they can be 15% under the actual cost up to 20% over. And finally, we have detailed estimates. Okay, these estimates are range from -3% up to about 5% accurate. So they can be slightly below or slightly above the actual result. There is a trade-off between the accuracy of your estimate and the cost associated in producing those estimates. What you tend to see is that as the accuracy increases, the cost increases as well. So if we have a low accuracy, we tend to have a low cost associated with it, and as we increase the accuracy, the cost increases significantly. It turns out that this is not a linear relationship. It is in fact exponential. We start off with low cost representing low, or low accuracy representing low cost, and as we increase the accuracy, the cost just takes off. For that reason, I actually drew that backwards. We should see it look something much more like that. Okay, so with this then, there are several types of estimates that we can perform. There's what's known as a per unit estimate. The examples that you see in the homework and in the textbook are all based on real estate. So one typical problem will say, assume that the real estate or office space in Ellensburg goes for approximately $50 a square foot. Okay. If we need an office that's 2,500 square feet, how much will it cost? Well, then we go through and say, well, by per unit estimated techniques, we'd have $50 per square foot times the 2,500 square feet. So we'd have 50 times 2,500. Keep in mind that you can use the per unit analysis techniques that you have learned in chemistry and physics and elsewhere to perform these multiplications. But we would see that we have a cost estimate of about $62,500. Actually, no, I'm sorry, that should be $12,500. Maybe with the extra zero there. Yes, $125,000. Okay. So again, used quite extensively when we're considering real estate, office space, lot sizing, and so on and so forth. And in fact, that's the types of problems you see in the homework relating to this per unit estimate technique. Okay, in addition to per unit estimating, we can do segmented estimating. This is what the book calls a divide and conquer. What you're doing here is breaking a product down into its constituent pieces to determine the cost of each piece. Okay, so what we could do is take a look at a lawnmower. We could say that lawnmower has a motor that costs $75, 4 wheels that cost $5 each, so $20 total. The frame and handle assembly might cost another $30. So by using the segmented estimation process, we can see that the cost associated with producing this motor would be $125. We could then go through and use that per unit cost in order to factor into the cost equation that we talked about earlier. Okay, after we talk about segmented costs, next thing we can do is look at cost and price index. What this does is it essentially allows us to use our proportional reasoning to determine the cost of or at different times of a product. If we have a product with a price index associated with it, we can say that the cost at time A compared to the cost at time B is equal to the index assigned to that product at time A versus the index assigned at time B. So a good example of this is say that a pump was purchased in 2000. So in the year 2000, we purchased a pump for $500 when the cost index was 200. In 2010, we want to know what the cost if the index is now 550. So what we can do is use this cost and price index model to say that while our cost in year A, which is in year 2000, was 500, the cost in year B is in 2010 is unknown, but we know the relationship between the cost index. In 2000, the cost index was 200. In 2010, the cost index was 550, and therefore we can see that the cost in 2010 is equal to, throwing some algebra at this, we have, let's see, it'd be 500 times 550 over 200. So we end up with a cost of $1,750 in 2010. Whenever you talk about an index, this is what you're talking about. So just kind of keep that in mind as you're going through the homework and responding to some of these questions. This idea of an index has been implemented in what is referred to a power sizing model. What this does for you is it allows you to relate two similar pieces of equipment that might vary in the size associated with it. For example, if we have a generator that, if we have two models of a generator, one that's capable of producing 10 kilowatts, the other is capable of producing 15 kilowatts, then we can use this power sizing model to compare those two generators to determine which is, or what the associated cost of the alternate model would be. So this model is set up by saying that the cost associated with the first model is compared to the cost associated with the second model. And this is related to the power sizing ratio, which is the size of A compared to the size of B raised to an exponent x. X is defined as the power sizing exponent. And in chapter 2, there is a table that lists out all of the power sizing exponents that you'll need. This is particularly valuable for you on problem number 9. You will need to look in that table to determine what the power sizing exponent is for the problem or the scenario that they provide you in problem number 9. As you can see, this is just straight away a plug-and-chug type of situation. As we saw in the previous example, if you're given the sizes associated with the first and second model and the cost of one of the models along with the power sizing exponent, you can solve for the other model just by applying some simple algebra to the problem. I'm almost out of time here, so I want to finish off the last couple items here. In addition to these other estimating techniques, there is a learning curve estimation that is sometimes employed in manufacturing settings. What this does is it provides an estimate of how long it should take to produce a product. If 200 have been produced previously. If n, I will leave it as a variable, if n have been produced. This is set up as an exponential expression. So we say that the time to produce the nth product is equal to the time it took to produce the first piece of product times n to the b. This b term is what's known as the, give me a second, this is the learning curve exponent. Okay, what you see here is that learning curve exponent should be negative, okay? The reason for that is if it is positive, then this will be growing instead of shrinking, and that means that each piece of product you produce takes slightly longer than the previous one. So when you're going through and calculating this b term, make sure that it in fact turns out to be negative. Otherwise, you know, each successive item is taking slightly longer than previous, and that would probably not be a good feature. Okay. If the problem does not give you the learning curve exponent, then you'll have to calculate it. And it turns out that you can calculate it by saying that it is equal to the log of the learning curve as a percent divided by the log of 2. So if you say that each item is going to take you 80% of the time it took you to produce the previous item, you can go through and say that your learning curve exponent will be the log of 0.8 divided by the log of 2, and that'll give you your learning curve exponent. So with this provides you a brief overview of Chapter 2. At this point, you should be able to complete quizzes 1 and 2 over Chapters 1 and 2, as well as assignment number 1. That is the assignment related to Chapter 2. Please make sure that you're moving through the material and not allowing yourself to get behind. Again, I'll probably say this in every video. You need to make sure that you're allocating adequate time to make sure that you stay caught up with the material so that you don't allow yourself to get behind and try to cram through it last week or 2 of class. So with that, I will be back soon to provide you a real quick overview of Chapter 3.